Hello students, welcome to the class of digital signal processing. We were studying DTFT, discrete time Fourier transform. So we were doing the properties of discrete time Fourier transform. We have already done some of the properties. This is the major formula for the discrete time Fourier transform. You are representing the discrete time signal with x of n, and when you take the Fourier transform of that, you represent it with capital X of e to the power of j omega somewhere, and somewhere you use just x, capital X. Inside the bracket, you write omega. The formula that is what applicable for DTFT is n is equals to minus infinity to infinity. The summation is ranging from minus infinity to infinity x n e to the power of minus j omega n. The inverse discrete time Fourier transform. Here you can see it is given as 1 by 2 pi minus pi to pi x of omega e to the power of j omega n d omega. Here it is a minus sign, here there is a plus sign. More than that, the very, very important thing that you have to notice here is that this is a discrete time signal which you are, the xn is a discrete time signal, and when you take the Fourier transform for this, then the signal is coming out to be x of omega. Now, this x of omega is a continuous signal. So, continuous and the discrete time Fourier transform stands for discrete and aperiodic signal. So, this signal x of n is discrete and non-periodic. When you take out the Fourier transform, it becomes continuous and periodic. So, this is an important thing. You can also understand this thing from the formula that is given here. It is 1 by 2 pi minus pi to pi. That means it is taken out for the interval of 2 pi only. Why? Because it is periodic. And also here it is the sign is given off for an integral which is used for continuous functions. And here you can see the sign is given as a summation which is used for discrete functions. So this is one way of remembering uh, uh, the spectra of these and the signal representation. So we already did the linearity property, which is same as the property which was used for the transform or DFF. Then it is the periodicity property. We also did this one. It is periodic by with the interval of 2 pi, the DTFT of the signal. Okay. Then the next one was frequency shifting. That means if you are multiplying the signal with exponent of something, then in the frequency domain, or the after you take the DTFT, the signal gets shifted in the frequency by the same amount with which here it is multiplied. So it will get shifted by pi by 2 over here. The next question was on the time shifting property. So these two property you can take opposite of each other. What happens when you are multiplying in the time domain, when you are multiplying with certain frequency, or means in the time domain if you are changing the frequency, then in that case in the frequency domain there is a shift in the frequency. And here, what does it mean? That if in the time domain you are shifting the signal by some time amount, then in that case, the frequency in the frequency side, the DTFT side, the signal will be shifting by the same amount in the frequency. In order to understand mathematically, if you're multiplying here, that is called the frequency shifting. And if you are just shifting this n to n plus 2 or n minus 2 or n minus something, then that is the time shifting. We already did this. So now the next part that we have to do is, we have also done this part, conjugation and time reversal. So when you take the DTFT of the conjugate of the signal, it will become x star e to the power of minus j omega. In this case, it will simply become x of e to the power of minus j omega. Here there will be, when you will take the DTFT of this one, it is x of e j omega, then again minus e to the power minus j omega, and then again the conjugation. Here just e to the power of minus j omega. We did the differentiation in frequency property, which says that if you are multiplying with n in the time domain, then whatever x of e j omega you have got, that will be differentiated. Means x of n will be having x of e j omega. Then if you multiply here, then that side you are going to differentiate it once, because once you have multiplied n. If it would be n squared, then 2 times you are going to differentiate it. For the symmetry property, there were many parts, real and even, real and odd, all those. For different type of signal, you had different uh, property in the frequency domain. Now today we will start with this one, that is convolution in time domain and convolution in frequency property. So the two signals are given to you over here. xn u is equal to un and h of n is equal to 0.5 raised to the power of n un. Now they are asking you the DTFT of yn. Yn is what? Yn is xn convoluted with hn. So in the time domain, you are convolving the two signals. So when you take the DTFT of yn, then the individual DTFT of xn and hn will be simply multiplied. So that means convolution in the time domain results in multiplication in the frequency domain. Same way, the opposite is asked here. Here you are multiplying in time domain. So what will happen that the Fourier transform of this xn and yn, that is x of e to the power j omega and y of e to the power j omega, they will be convoluting. So let us see this. So the signal given to us is, first is, you have to keep in mind that we have been given two signals, xn is equal to un and yn, it is hn. Okay, so hn, h of n is equal to 0.5 raised to the power of n un. Now, they are telling you to find out the DTFT of yn. And what is yn? DTFT of yn, where yn is given as xn convolution okay. So yn is given to us as xn convolution with hn. So one method could be to take out the convolution of xn and hn and then find the Fourier transform or DTFT of that, right? But with the property, it becomes easier. How it becomes easier is, the property says that you don't need to find out the convolution part. You can directly find out the DTFT of yn. So DTFT of yn will be written as y of e to the power of j omega. DTFT of yn will be y of e to the power of j omega. That will be equal to the DTFT of x of e to the power j omega into simple multiplication with h of e to the power of j omega. Now, first of all, we will take out x of e to the power of j omega. You know the Fourier transform DTFT formula, n equals to minus infinity to infinity xn e to the power of minus j omega n, right? Now, xn is given to us over here as un. So, this is going to range from n equals to 0 to infinity. Un, the value is 1 everywhere, e to the power of minus j omega n. Now, the first value for this one is going to be 1 when you put n equals to 0. Second will be e to the power minus j omega. Third will be minus e to the power of minus 2 j omega. So, this is going to be a infinite geometric series with the first term as 1 and the common ratio as e to the power of minus j omega. So, this is x of e to the power of j omega. Now, the second one is h of e to the power j omega. Now, the second one that you have to take out was h of e to the power j omega, where hn was given to us as 0.5 to the power of n un. So again, it was multiplied with un. So we changed the limit from minus infinity to 0 to infinity. So it is becoming 0.5 raised to the power of n e to the power of minus j omega n. Now we will put 0.5 and e to the power of minus j omega together and whole to the power of n equals to 0 to infinity. If you see this, if you put 0, then the value is 1. If you put 1, n is equal to 1, the value will be 0.5 e to the power minus j omega. If you put 2, 0.5 square e to the power of minus 2 j omega. So basically, this is also a geometric series with first term as 1 and the common ratio as 0.5 e to the power of minus j omega. So this is what h of e to the power of j omega for us. H of e to the power of j omega. Now you have to find out the DTFT of y of e j omega. You have to find the DTFT of yn. DTFT of yn. This was your question. That will be denoted by y of e j omega. And we also found out that y of e j omega is equal to x of e j omega into h of e j omega. Now we have already calculated this. So this one was 1 by 1 minus e to the power of minus j omega. And this one is 1 by 1 minus 0.5 e to the power of minus j omega. Now you can multiply this. Simple multiplication will do, and put the answers, or you can keep the answer till here also, but do one more step, that is multiplication is required here. 1 by, so what is it is going to become, or you can do it one more way, that first you write it over here in a more simpler format, then it will be e to the power of j omega divided by e to the power of j omega minus 1. And this side it is going to be 0 e to the power of minus j omega divided by e to the power of j omega minus 0.5. So here at the down, next step will be so the next step for us is going to be what? This is e to the power j omega. So it is going to cancel 1 by e to the power j omega minus 1 and e to the power j omega minus 0.5. So this is the DTF. Then do it one more step, but it's okay till here. Now let us see the different one, convolution in the frequency property. So here you see it was convolving this in the time domain. Now you are multiplying this two in the frequency domain. So when you take out the Fourier transform, then you will have to do the convolution. So one thing you can do is you can easily multiply these two and then take out the Fourier transform. That will be easier case. But since we are doing here the property, we will do the convolution in that way. Okay, let us see. So xn is given to us. So this is the opposite of the previous one. So xn is given to us as 1 and 2. And yn is given to us as 3 and 4. Now they are telling us to find the DTFT of Zn. DTFT of Zn is asked, where Zn is equal to what? Zn is equal to xn convolution. Is it convolution? Let us see once. It is not convolution, it is multiplication. So in time domain, you are multiplying these two signals, xn into yn, simple multiplication. So the property says that when you take out the DTFT of Zn, that is z of e to the power j omega, that is going to be the convolution of x of e to the power j omega convolved with y of e to the power of j omega. Now when you do convolution, what is it? How you do the convolution? For this, you know, it is a continuous signal. When you take the DTFT, it becomes continuous. So you can write it, change the parameter over here, e to the power j theta into y e to the power j omega minus theta d theta. And since it is continuous from minus pi to pi, and the 1 by 2 pi. So this is the full thing that you will have to do to find out the z of e j omega. Okay. So now if you see, one thing you can do in this case is that since they have multiplied previously, so if you multiply this, then Zn is going to come as, just we will do for the sake of verifying. So point to point multiplication, 3 into 1, 3 and 4 into 2, 8. Now if you take out the Fourier DTFT of this one, So directly take out. So in this case, this method becomes easier, right? Because convolution is a bit calculated. So this method becomes easier. So now if you take the Fourier transform of this one, then the answer is going to be 3 plus 8 e to the power of minus j omega. But here, since we are trying to verify the property, we will do this part also to some extent. Now, see it. So first one was, xn was given to us as 1 and 2. So x of ej omega will be what? 1 plus 2 e to the power of minus j omega. Same way, yn was given to us as 3 and 4. Yn was given as 3 and 4. So y of e to the power of j omega will be 3 plus 4 into e to the power of minus j omega. Now, according to this formula, if you write it in terms of theta, then this is going to be 1 plus 2 into e to the power of minus j theta. And if you replace this omega with omega minus theta, then you will have to do the same thing for this side also. 3 plus 4 e to the power minus j omega minus theta. Now we will do the convolution. So while doing the convolution, what is going to happen? 1 by 2 pi minus pi to pi x of e j theta into y of e to the power j omega minus theta. This is omega minus theta d theta. So you are integrating with respect to theta. Keep this in mind. Now write down the values. Minus pi to pi. 1 by 2 pi is there. 1 plus 2 e to the power of minus j theta multiplied with 3 plus 4 e to the power of minus j omega minus theta d theta. Fine. Now multiply this part. So first one is going to be 1. Sorry. So first it has to be multiplied with 1. So 1 into 3, that will be 3 plus 4 e to the power minus j omega minus theta plus 6 e to the power minus j theta plus 8 e to the power of minus j theta into e to the power of minus j omega minus theta. So let us first multiply it properly so that we get a smaller, simpler term to integrate. 3 plus 4 e to the power of minus j omega minus theta. Okay. Now this minus j omega minus theta can be written as minus j omega into e to the power of plus j theta. Right. So we can write this one as 4 into e to the power of minus j omega into e to the power of plus j theta. Right. This is the same thing, but that won't hamper you for the integration process. So let it be as it is, e to the power minus j theta plus 8. This one, let us do it completely. E to the power minus j theta into e to the power minus j omega into e to the power of plus j theta. So what happens is this and this one will become 0 because minus j theta plus j theta will become e to the power 0. That will become 1. So finally what you have over here is, these are the terms for us. 3 plus 4 e to the power minus j omega minus theta plus 6 e to the power of minus j theta plus 8 e to the power of minus j omega. Now this has to be integrated in terms of d theta. This is from, very important thing, this is from minus pi to pi, 1 by 2 pi. So this term over here, this one and this one is becoming 0. Because see, this is the integration over minus pi to pi. So when you take that full thing, then the whole thing is going to remain that only sine will come, and sine of 0 is 0. So this one and this one is going to be 0. And here what happens is it is integrable with respect to theta, not with respect to omega. So this one will remain. Now this is like a constant over here. And this one, this 3 is also a constant, but you are integrating with respect to d theta. So let us see what is going to happen after this. 1 by 2 pi, you are having over here 3 theta, that is going from minus pi to pi, and you are having 8 e to the power minus j omega, and again you have this theta which is going from minus pi to pi. So basically you have 2 pi over here and 2 pi over here. So if you take out those 2 pi's, so 2 pi is going to cancel with the 2 pi downward, and what remains is 3 plus 8 e to the power of minus j omega. The same thing which you got by simply multiplying and then taking out the DTFT. Just see it over here. See, you just multiplied it first and then took out the DTFT. So for this case, the property, using the property is better. For this case, just multiply it and then take the Fourier transform. That is much easier. Both are the opposite of each other. That means the main thing that you have to keep in mind that multiplication in time domain results in convolution in frequency domain, and convolution in time domain results in multiplication in the frequency domain. That is the most important point. Now the next is correlation theorem and modulation theorem. So for correlation, the same thing is happening. Correlation means you are finding out how much the two signals matches, or how much is the two signals same. The similarity is measured between the two signals. And in case of convolution, we are measuring the sum of shifted impulses. So let us once see how to find out the cross correlation and what is the DTFT cross correlation property. How to find out cross correlation, that we are not doing here right now. We will just be using the DTFT property because it will become too long. So correlation and convolution, I will be telling in a just how to find out correlation will be taught in the other class. So here how to use the DTFT property. So here the question says you that x of n is equal to 1, 2, and 3, and y of n, right? Y of n is 4, 5, 6. Y of n is equal to 4, 5, 6. So these two signals are given to us, and they are telling us to find out DTFT of correlation between these two. So that correlation is denoted by R. Since these are two different signals, so it is cross correlation. Cross correlation between these two is denoted by R. X and Y, it is between X and Y, and it is in discrete time. So this is this one. Now here what we write is, the method is X n plus R convoluted with X of n plus some other value you will use, not R, because R we are using for denoting this cross correlation. So we can take it as something else. Let us take it as m, as it is given in the question. X n plus m, y star, see, y star n will be there. Y star n, that means conjugate of y. So what is the DTFT property? This is just the correlation, meaning of correlation or mathematical definition here which is being said. But in case of the property, how we are taking the DTFT of Rx by n, in that case, what will happen is, you will take the DTFT of x of n, DTFT of y of n, but take the conjugate of the DTFT of y of n. So, Rxyn, if you take the DTFT of this, then what you need to do is the individual DTFT x of ej omega multiplied with y star e to the power minus j omega. So, what is our question? Xn is given to us. We can easily find out x of ej omega now. So, it will be 1 plus 2 e to the power minus j omega plus 3 e to the power of minus 2 j omega. How I am getting this? I think everybody knows it. Okay, I'll do this for yn. So yn was given to us as 4, 5, 6. So anyways, y of e j omega you have to take out. The formula is minus infinity to infinity, y of n e to the power of minus j omega n. But here, this is a discrete time sequence and the values are present only for 0, 1 and 2. So y0 e to the power minus j omega 0 plus y1 e to the power minus j omega 1 plus y2 e to the power minus j omega 2. The value of y0 was 4. This will become 1. Value of y1 was 5. This is e to the power minus j omega. Value of y2 was 6. This is e to the power of minus 2 j omega. Now for doing this, what you have to do is you have to take the first take out e to the power y of e to the power of minus j omega, and then we will do the conjugation of that. Fine. So if you do the y of y star e to the power of minus j omega, this is what you need to find out. So it will become 4 plus 5 e to the power of j omega plus 6 e to the power of 2j omega. And now we are going to multiply. So we have to just take the conjugate of it. Now we will multiply this x of omega e to the power j omega with y star e to the power of j omega. Okay. So here what we will be doing is y star e of j omega, that is coming to be, you have to multiply this one. So 4 plus 5 e to the power j omega plus 6 e to the power of 2j omega. This is the y star, the conjugate of y of j omega. And the x1 was what? X of e j omega was 1 plus 2 e to the power minus j omega plus 3 e to the power minus 2j omega. 1 plus 2 e to the power minus j omega plus 3 into e to the power of minus 2j omega. Now you just need to multiply it term by term. Means 1 multiply with all, 2 e to the power minus j omega multiply with all, and this one also. So that will give you the answer for this problem. Okay, the next property is the modulation theorem. So what does the modulation theorem say? That you have to basically shift here. So here the question is given to you as y of n is equal to xn cos omega naught n. So that means the modulation theorem is applied when the signal is multiplied with a cos or a sine. So this is your original signal. It is multiplied with cos omega naught n. So what happens is that when you take the x of e j omega, this is the DTFT of this one, then you find out the DTFT of y of e j omega. It will be x of e j omega plus omega naught, and this side it will be x of e to the power j omega minus omega naught. So this is the modulation theorem property. Why does this happen? Because you can write cos omega naught n as, see, now we will do it both the sides simultaneously. It will be much easier to see. Yn is equals to x of n cos omega naught n. So you can write this cos omega naught n as e to the power j omega naught n plus e to the power minus j omega naught n divided by 2. And this is x of n. This is y of n. Now if you take the DTFT on both the sides, then this is going to become y of e to the power j omega. Take half outside. Okay. Now let us, at this point, we will go at this point a little later, right here, yn. But let us do this part. That will be much systematic. So let us write for this time. Let us write it this only. Now it will be xn e to the power of plus j omega naught n, right? And this one will be plus xn e to the power of minus j omega naught. Now, if you take the Fourier transform or the DTFT on both sides, then this side is y of ej omega, which you have to find out. And this side it is half. By using the frequency shifting property, if this has the DTFT x of ej omega, then it will be shifted e to the power j, this is plus, so it will become minus omega naught plus x e to the power j omega plus omega naught. So this is the modulation property, which is very useful in communication system. It will shift the frequency. Here means that the frequency is going to increase, and in the spectrum you are going to see that it is shifting. So that's all about the property of DTFT. In the next class we will be doing DFT. So we will start first with the difference of DTFT and DFT. Once I'm saying in a very short sentence that DTFT is discrete time Fourier transform, right? So whatever you get as the answer of DTFT, if you sample it, that will give you DFT. So here in case of DTFT, the signal, the original signal xn was of infinite length and discrete time signal, right? And after you did the DTFT, it become continuous and periodic within an interval of 2 pi. Now here, when you do the DFT, from the 2 pi interval, you will take only certain points, say n points you will take, and that is why it is becoming of finite length. So the major difference between DTFT and DFT is that one is of finite length, DFT is of finite length, and it is taken, DFT is calculated for finite length signals, and you have finite set of points in the frequency domain also. And here in one sentence, you can say that DFT is the sampled version of DTFT, and it is easier for computation. So in the next class, we will start with the formula of DFT, and then we will be doing the properties. Thank you, everyone.